I'm going to share my screen, and I'm going to put in the chat the link to the slides. If you want to follow along, you can also follow there if you're lucky enough to have a computer. All right, so thank you again for the invitation. And as Kate mentioned, what I'm generally interested in research is this interface. This interface between those new methods that are emerging from the deep learning community and the physical models that we want to constrain and that we want to use for doing science. And so what I'm going to try to show you today is my take on how to best get those two to work together in order to avoid making mistakes or suboptimal use of one or the other. So I'm going to go very fast on the general motivation for all of these things so that we can spend more time on the methodology itself. But the general motivation is that, as you may be aware, there is a range of new surveys that are coming online now and in the near future. And so my favorite one at the time is this Rubin Observatory, which you have an animation of here, which is going to be a giant robot telescope that is going to take systematic images of the sky over a period of 10 years. Let me show you quickly how this is going to look like. The telescope is going to take, automatic pointings in the sky and go back to the same point of the sky every few nights or so, and do that every night for a period of 10 years. So that's a huge amount of data. Each night, it's going to be about 15 terabytes of data. And it's going to observe almost half of the total sky. And beyond that, it's also going to open a new, realm of interesting astrophysics that you can do by looking at transient events with this time series that is going to be created by the telescope. So why do we do this? Is because obviously this is a huge potential for new discoveries and for constraining cosmological models in particular, things that I'm interested in. But it also brings a lot of new challenges. And the best way, without going into details of illustrating those challenges that I found, is to show you what the data is going to look like. So what you see here is an image of a galaxy as it could be observed by a previous generation instrument like SDSS. And the SDSS sky was very, let's say, simple, even though you could already do a lot of things with it. But essentially, everything was more or less a blob. And then as you go towards newer and newer generation of instruments, the sky becomes increasingly more complex. So this is the same galaxy as seen by DES, and already you can see more objects, and you can see that the central object has more features. And when you move to what the sky is going to look like for an instrument like Rubin, it becomes even more complex. This is, I think, a metaphor for what happens at every steps of the analysis, is that the data is intrinsically more complex and difficult to handle. So a concrete example of things that we have to deal with now is the fact that all of those galaxies here start to overlap with each other on the sky, which makes it so much more difficult to measure precisely their individual properties. All right, so the data is more complex. We have lots of it. And the naive question that you could ask here is, can AI, with quotes on AI, solve all of our problems? And here, this is my intro to the rest of my talk, is that maybe, but if we use it correctly. And to show you what I mean by that, I want to go back to a very simple example, a very simple problem, and we'll try to understand it and see how we can go beyond what's the simplest approach that you could take. So this motivating example that I'm taking here is the problem of image deconvolution. So this is something that you will find everywhere if you do astronomy, right? Because you have to take into account the point spread function of the instrument. So the problem in general is that we observe some data Y, and there is some true galaxy on the sky that we don't actually observe. And between this true galaxy and what we have is the instrumental response of the telescope, so the PSF. Usually you also have some additional noise. So this is what it looks like. This is a high resolution of a galaxy, but this is what you would see from the ground. It's blurry because of the PSF, and you have extra noise due to the fact that you don't observe for an infinite amount of time. And so a naive approach here might be, okay, I'm just going to take one of those deep neural networks that I've heard about so much, and I'm going to train it so that I feed it this low resolution image. And I'm going to ask it to recover this nice high resolution image. So remove the effect of the instrumental response and remove the effect of the noise. All right, so why not? You can try to do that. And actually a lot of papers I've tried to do that, but let's see what happens. So the first step that you would take here is to start assembling your training set. So how do I do that? For instance, I have either some space-based observation, some Hubble observation that I can take as my reference high-resolution image, or I can run simulations. But at the end of the day, I can assemble a training set of pairs of objects, the nice resolution image that I don't see, and the degraded resolution image that I get from the ground. And I can make a bunch of those pairs of images here. The first important thing to realize here is that when I build this training set, I put in some hard-coded assumptions about what is going to be the instrumental response and what is going to be the noise in my observations, because that is a decision that I need to take when I get those Y examples that I build into my training set. Okay. And so then now that I have my training set, I can train my neural network. And usually the way this is done is by, let's say you can try to train a regression network so that you train it to recover from this degraded image the best guess of the true image under typically an L2 norm. So you penalize the mean square difference between the answer from the network to the true value. All right, so that is super easy to do. You can do this in 10 minutes in a notebook. And here is what you will get. You have this low resolution image, you feed it through your neural network, and it gives you this image here. Okay, so it's doing things, it's removing the noise, it's removing part of the PSF, but here is what the true galaxy looks like. And we see that there is additional features in the true galaxy that we don't find here. And so my question here is that we notice that the answer from the network is not the truth. But then what is it? How can we explain that we cannot recover the truth here? So one explanation might be that my network is suboptimal. I'm training it to do a task, but it's not managing to do that task well enough. But actually, the main reason for this discrepancy has to do with the intrinsic question that we ask of the network. And let's try to see what that question is and if we can understand this output here. So I can go back and look at my loss function and try to understand it in a different way. So I won't go into all of the math, but the main idea that I want you to have here is that I can understand this loss function, which can be thought of the question that I ask of my network in terms of this rewriting. And at the end of the day, what it means is that the optimal network is trained to estimate the mean of this distribution. And what is this distribution? It's the set of all possible galaxy images that are compatible given some input data. So a perfect network, and you can never reach a perfect network, but you could imagine a perfect network. The thing that you get out of perfect network with this loss function is the mean of this distribution here. And so is that a good thing to have? Well, you can try to look at it on very simple examples. And here, what I'm showing you is a very simple example of X and Y on a 2D plane. So you have some X's here, actually it should be Y, and some X's here. And I'm training a neural network to do this regression task for given, let's say, those data points that I have here. I'm training it to do this regression task under this L2 loss function. And what the network gives me is the output will be this blue line here. But the true underlying distribution that I drew this sample from is this shaded region that you see here. So you can see that the network under this L2 loss is going to give me an answer that can be far away from the most probable answer, which would be more closer to this ridge here. But there is nothing wrong in the network. It's just what we've asked it to do. And I can actually overplot the analytic mean of this distribution, and it follows it pretty closely. But I can also change my loss function. And so instead of an L2 norm here, I could, for instance, have an L1 norm. And the answer of my network is going to change again. And it's just because I am actually changing this math here. And the network is now optimized as to find the median of this conditional distribution. So my main point here is that there is nothing wrong in using this network, but you need to understand the question that you're asking of it. And what is interesting to notice is that if you do L2 or L1 regression, you will never actually reach this maximum probability region, which should be more or less here. So you'll make it, you get an answer that is suboptimal. And if you want to know more about this, I have a blog post and a collab notebook with examples of it that you can find in the slides. All right. So I think this is something interesting to keep in mind, but you can also try to understand it from a different point of view. This distribution of possible solutions given the observations, I've not said what it is, but actually this corresponds to a Bayesian posterior distribution. So the set of all possible answers that match the data, which you can usually split using Bayes' theorem into a likelihood term that tells you how probable the given observations are given a solution, and a prior term that gives you how probable your solution is from prior expectation. And so what that means is that your neural network that you've trained this way is actually solving your Bayesian inference problem, but it's using it's learning implicitly the likelihood and the prior. And it's learning it from the training set that you've provided it to him. So when you're using a neural network in this fashion, you're doing Bayesian inference in a way, but you are not only hard-coding the priors, the likelihood, and you're also asking of the network to do the inference part. So you're asking a lot of the model. And the nice last thing that I mentioned is that the answer from the model is going to be a point summary of this full distribution, this full posterior, and you lose all of the uncertainty quantification that you care about when you do Bayesian inference. And so these are the limitations of using neural networks as black box in this way. And if you want to remember this, I'll show you this image. This approach of using a neural network as a black box is a non-stop ticket to the danger zone, what I call the danger zone, is when you're trying to do estimation, but you don't have a good estimate of your error bars, or you think you're very precise, but you can very easily be not accurate at all in your prediction. And so, for instance, how can this happen? Maybe the priors that you've used for training the model does not actually apply for the data that you then infer, that you then apply your method in. Or maybe the likelihood that you've implicitly trained the model on is not going to be the correct one when you apply it to the data. You would never know. You can still apply the network, but it's going to give you an answer that is offset from the true values that you care about. All right, so how do we avoid this? And that's going to be the main point of my talk today. The way to avoid this is that we want to look at those three considerations: cosmology, physics, deep learning, and uncertainty quantification. And we want to target these center regions. So if I'm just interested in, astrophysics, cosmology, and deep learning, that's where I will find applications that are more around astronomical data reduction. And so typically finding rare events like gravitational lenses or classifying galaxy morphologies. If I'm just interested in doing uncertainty quantification and deep learning, I will find the domain of Bayesian neural networks. And if I'm just interested in doing physics and uncertainty quantification, that's where I find the traditional Bayesian inference things that we do in physics. And what we'll try to do in this talk is to remain right in the center. So keeping everything that we love about Bayesian inference, but using deep neural networks to try to make inference possible where it was not possible before. And that's going to be the main theme of my talk. All right, I want to give you several examples of where you can apply this idea. And I'm going to start with this one because it's related to this first example that I used to introduce these notions. So inverse problem, what do I call an inverse problem? So inverse problem is a very generic classes of problem that you can always write this way. You have some observations Y and some true signal X that you do not have access to, but you want to recover. And in middle, you have some operation A that degrades your information. And so, for instance, in our first example, this was this blurring operation that you get from the telescope. And so the problem with those inverse problems is that most of the time, A is going to lose some information, which means that you cannot directly invert it. And you also do not have a single solution to your inverse problem. And just to show you a couple of examples, a few examples of these situations, this can be, for instance, a deconvolution problem. This is what we saw in the first slide, in the previous slide. It can be things like inpainting. You have missing data and you're interested in recovering what's in the middle, or just denoising. In this case, A is the identity, but you just have a noise term that you want to get rid of. So my point here is that they are very generic and you can find them everywhere. So how do I solve this type of problem if I'm, a cosmologist, so I'm biased towards Bayes, let's say. So the way that I want to think about this is from this Bayesian point of view. So I'm not interested in point estimate. I'm interested in finding the full distribution of possible solutions that match my data. And with Bayes, you usually split this problem into two terms. The first one is the data likelihood. And what I want to stress here is that usually you know this likelihood analytically. There is no guessing games. There is nothing to learn. This guy, you can learn it from physics, and you can use physics to write it down. And I'll show you examples of where you can do that. And then you have a prior term here that helps you close this formula here. And that's where you can put in your prior knowledge of what your solution should be. But when you have those concepts in hands, then you can do things like solving this problem, finding a point estimate for this inverse problem. So for instance, finding the maximum a posteriori solution, the one that is maximally probable under both your prior and your likelihood. That gives you a point estimate of the solution, but you could argue this is the best point estimate that you could get. Or you could try to solve the full inference problem and target the full posterior, and so get sample, so possible solutions that are compatible given my data and my prior. All right, and so these we know how to do it. We know how to do this. We have algorithms to solve this problem. So then, why do we need deep learning here? And so the question you should always ask when you meet a Bayesian guy is how do you choose your prior? Because this is usually the most tricky part of this problem. And the choice of prior can heavily influence your solution. So the thing that you could directly realize here is that you need a prior that you can actually numerically evaluate on your solution in order to use it within those algorithms here. And so this fact that you needed to evaluate numerically the prior has been a limiting factor for many years of the complexity of the prior that you could possibly think of for using for solving those inverse problems. So I'm not going to go through all of those examples here, but the one that we use most often in cosmology is this Gaussian prior. So assuming that the probability of my data can be described as a Gaussian field. So essentially, this is, you can think of it in different ways, but this is just assuming, for instance, the power spectrum of your signal. And why do we do this is because this is very easy to compute, this log p under a Gaussian model. All right, so that's nice, but let's have a look at the data that we're trying to analyze here for these modern surveys. This galaxy is not correctly defined by a Gaussian prior. It's not defined by those additional priors like the sparse prior or total variation prior that I mentioned before. And then the question becomes what to do in case where the data becomes more complex than those simple priors. And obviously, since we have this added complexity of the data, we are drawn to the question of, can we learn this prior from the data itself? And that's where deep learning can come in. And I'll show you how. And so the realm of deep learning that is interesting to us here is this general range of methods that are called generative modeling. So what is generative modeling? At the end of the day, is trying to estimate or model a distribution that is only known implicitly. What do I mean by an implicit distribution? Is a distribution where I don't know this log p of x. I cannot evaluate it numerically, but I can sample from it. So if you think of, for instance, I want to learn the distribution of what galaxies look like. I don't have an analytic model that tells me what this is this log p of a galaxy, but I can look at existing sets of galaxies, and I can use that to sample implicitly from this distribution. So at the end of the day, it means that I have access to a set of examples from that distribution. And then what I want to do is come in with a model, a distribution model with some parameters theta, and I want to match this distribution, this model distribution, to this implicit distribution that I only have access to from samples. So let's have a look at the simplest example that you can think of, trying to model a Gaussian. So this is a Gaussian, no surprises there. But here is what you would have access to in real life, not the Gaussian itself, but samples from that Gaussian. And so in 2D, one way that you can try to estimate this model distribution here is just, for instance, using a kernel density estimate, and you can get like a smooth estimate of this underlying distribution, and it would look like that. And what is nice is that when you've done this modeling, you now have access to this P of x. So you can actually numerically evaluate the probability of any point in this plane under this model distribution. So Francois, okay, that's nice, but you have an example of 2D here. It obviously works very well. Why did we need deep learning for this? Well, the problem is that this works well in low dimensions. You can do kernel density estimation in low dimensions, but when you go to high dimensions, things start to blow up. And this is known as the curse of dimensionality, or a consequence of the curse of dimensionality. So one way to think about it is to look at this image. Here you have a given number of points, either in a 1D space, a 2D space, or 3D space. In a 1D space, if I have 10 points, they will most likely be close to each other. So it's easy to do density estimation because the points are fairly densely populating your space. When I go to 2D, I can see here now that with the same number of points, I already have a hole here in my 2D space. And in 3D, it becomes even a bigger hole. And it gets worse and worse and worse as you go towards high dimensions, to the point where the space is essentially empty and you have no points anywhere. And this is essentially the curse of dimensionality, and the reason why the classical methods for doing density estimation fail in high number of dimensions. All right. And that's to me one of the most striking outcomes of this deep learning revolution, is the fact that now you can evaluate or estimate those densities in very high number of dimensions. And so here is just a quick recap of the road so far. Back in 2006, the best, the highest quality of samples or density you could build were for those MNIST digits. So these are digits that live in something like 700 dimensions. They are just black and whites, and they are fairly simple, fairly simple distribution to learn. And then around 2014, 2015, there was a phase transition really in how good you could build those density estimations with the arrival of some more evolved techniques. And so we went from modeling digits to modeling faces. With different techniques, you can model, better or worse different types of data. And then we almost reached a plateau a few years ago with this type of results. What you see here are not real faces. They are grown from a model that has been trained on faces. But what it shows you is that it actually learns correctly, to the point that a human cannot tell them apart. Very complex and very high dimensional data. So if we were in real life to convince you of this, I would try to do a live poll in real life, but I'm not going to try it here. But you'll just get the gist here. Is that these are two sets of images. One set is real and one set is fake, generated by one of those deep generative models. And I've tried this on many people at this point, and it's always very hard to tell which one is the truth. So I'm going to spare you here, and I'm going to just give you the answer, is that this one here on the left is a true set of a fake set of images, and the one on the right is true. The point being that for complex images, such as the one that we have in those astronomical surveys, we have models that can reach this level of complexity, and that makes it tractable then to compute this P of X for complex data. So that's really nice. But how do we use it to solve our problem at the end of the day? So let me show you this on the simplest possible case of an inverse problem. I'm going to go even simpler than the convolution. This is just a denoising problem. I have some observed data, I have some unknown data X, and I will have some additional noise on top of it. So how do I apply this approach of Bayesian inference and density estimation? So the first step will be to get examples from this data distribution X, so that actually corresponds to my prior expectation for what X should be. So let's assume that I have examples of those X's without data corruptions here, and they look like this. So my first step here will be to train one of those deep generative models to learn this distribution P of X. And what I will get is something like this that you see on the left. I now have a model that allows me to compute the value of this distribution at any point in this 2D plane. And you can see that it follows the distribution of the data that I had before. All right. So now if I want to think about what should be the answer to this denoising problem, that if I observe the noisy data points, it will not be within this distribution, it will be offset. So it will be somewhere a little bit offset from this distribution. And the goal of denoising is going to be to bring back this data point closer to the underlying data distribution. So yes, so to answer this question on the chat, the samples in this illustration have to be exactly representative of this true data, this perfect data distribution that I want to reconstruct. So we can talk about how you can get around that limitation afterwards, but this is the assumption here. And then when I want to solve my problem, the only thing, for instance, here that I can want to do is to try to find the solution X that gets close to the observed data point, but also that maximizes this prior expectation of what my solution should be. And so let me show you what this looks like live. And you can also run it if you have access to this notebook by clicking on this image and doing Shift-Enter. It's not super user-friendly, but you'll get the point. So what I'm showing you here in this purple region, this is my data point. And the size of the circle is kind of like how much noise I expect on this data point. And what you will see unfolding live is as I get a new data point here, which is offset from the true distribution, I solve this optimization problem on the fly, and my solution X here moves to get close to the observed data point and still remain within the data distribution. And this field that you see underneath here is what's called a score function, which is a derivative of this prior distribution. And another way to think about this is which direction I should go towards to if I want to get more likely under the prior. And you see that it tries to push the solution closer to this data distribution. And what is amazing here is that I only had access to a few data points, not to the true distribution itself. And you can see how it solves you can use it to solve the problem. All right, so that is the gist of how you go about merging those concepts together. And now let me show you an application of this from this paper here that was last year. There will be one on this probably within 1 or 2 weeks. So that's why I wanted to mention that, because you'll find it on the archive, and then you will have an idea of what this is going to talk about. So the actual astrophysical problem here that we're interested in solving is related to this effect of weak gravitational lensing. So you probably know that when you look at an object that is far away from us, if there is a massive structure along the line of sight, the light rays from these objects are going to be distorted. And that actually leads to a distortion of this image that we call a gravitational shear. So there is a true image, and then there is an observed image with some amount of shearing that happens. And so what we do in a lensing survey like Rubin or Euclid is that we measure the ellipticities of those galaxies, and those ellipticities are tracers for this gravitational shear field. So they are a noisy measurement of the shear. Let's put it that way. And so what we call mass mapping is to try to do this inverse problem. So we observe noisy estimates of the shear. So here you have a shear map that is exaggerated for visualization. And you can already see that there are some patterns in this map. And so the goal of mass mapping is to try to invert the lensing effect and recreate the mass distribution that gave rise to this shearing effect. And that's what mass mapping is. So going from shear to this thing that we call convergence, which is just a mass map. And luckily enough for us, there are relations that link the two, and you can actually condense them, so we don't actually need to know what they are. But you can write that down, surprisingly enough, again, as one of those linear inverse problems. So you have some measurements, the shear, and in practice, there will actually be noise on this shear that is linearly related to the convergence through this operator in between. The problem is that because you have missing data and because you have noise in the data, you cannot directly invert it. Otherwise, it wouldn't be a problem. And so it is, again, one of those ill-posed inverse problems. And I mentioned this because this is something that you can actually see in the news. So this was a paper that you maybe have seen from, I think, 4 months ago now. And that made the headlines of the BBC. We could talk a long time about this, but the point being is that you can do this mass mapping exercise on a lensing survey like DES and try to reconstruct a map, large-scale map, of the matter distribution on the sky. And this is what you see here, where you have a brighter clump. It's probably because you have a massive object. Another point that I want to make with this image is that they publish several maps. Why is that? It's because this is an inverse problem, depending on the prior that you use to solve it, you will get different solutions. So for instance, here, this is essentially a no prior direct inversion type of solution. This is a Wiener prior. And so this is assuming a Gaussian prior on the signal. And this is a sparse prior. And you see that those three maps are different. And you could ask me, well, okay, but which one should I trust? Which one is the best? And the point is, there's no good answer to that with those traditional methods. And that's what we're trying to overcome here. So how do we overcome this? Well, let's put on our Bayesian hat back again, and let's think of the problem from a Bayesian perspective. So what we're interested in modeling is the full posterior distribution of convergence maps given the measured ellipticity. And again, you can split it into a likelihood and a prior. So the likelihood term here, if you remember what I said before, this is where you can put all of your physical knowledge. So there is no guesswork here. I know what is the amount of noise that I have in my data. I can put it explicitly in my likelihood. I know what are the physics of gravitational lensing. I can put them exactly in my likelihood, and that allows me to relate, a given convergence map to the shear that I would expect to find on the data. So this guy, there is no guesswork. I know it's perfectly ish. But then I run into trouble when I need to define this prior here, this prior term, this prior on the convergence. And there is no analytic expression that allows me to write down what this prior should be. However, I do have access to physical models in the form of simulations. And so you can think of those simulations as one instance of those implicit priors that I mentioned before at the beginning of generative modeling. So I cannot analytically give you what is this P of convergence, so the probability of a given convergence map, but I can run simulations that will give me examples of those of convergence maps under my physical model. So it's still completely physics-based, but now I need a tool to go to use these implicit priors in a way that allows me to solve this Bayesian inversion problem. And that is exactly what we've done in this work. We learn the prior from simulations. So we turn this implicit prior into something we can actually handle for Bayesian inference. And then we sample this full Bayesian posterior. That's as simple as that. So actually, no, it's not that simple. One thing that you now have to solve in practice is how do you learn this prior efficiently for very high dimensional data, and then how you do this inference on convergence maps, which are actually very high dimensional objects as well. So you need to do inference over hundreds of thousands of dimensions. That's not trivial. But one of the very interesting realizations that we had in this project is that when you try to do inference, the only thing that you actually need to know is the score function that I've already mentioned. So the derivative of your prior or complete log posterior with respect to your solution. And one way to think about this is that if I want to do gradient descent to do my maximum a posteriori optimization, this is the algorithm that I need to use. And the only thing that comes up in this algorithm is the score function. And the same thing for some type of gradient accelerated Monte Carlo algorithms, it's going to be the same thing. And here is another visualization of the score function here. You have the density here that you want to model from your prior, and the score function is going to give you those arrows here. And so that was one of the main realizations working on this project, is that the only thing that you need to model is this score function. So how do you model this score function tractably in practice with a neural network? It turns out it's extremely simple to learn the score field. And the only thing that you need to know how to do is to train a denoiser on noisy Gaussian data. So how does that work? Let's say that I have examples from my implicit distribution, X. So in my case, perfect simulations. I can add some Gaussian noise onto my simulations to make noisy realization of those convergence maps, let's say. And then I can introduce a neural network with the explicit task of recovering the not noisy map given the noisy map, and also given some knowledge about how much noise I've introduced in the data. So you find again, this L2 regression that we had already at the beginning of the talk, but now it's used in a different way. It's used in this context. And what turns out is that if I train an optimal denoiser under this loss function, what the denoiser will learn is an update of your noisy example that is directly related to this score field. So the derivative of this log distribution. And so another way to say this is that I can learn my score function by learning a denoiser. And here is what this would look like on some simple data. I have some perfect examples from my implicit distribution. I noise them, and I train my denoiser to recover this image here on the right, which is without noise. And the output of my denoiser, this thing in the middle, is actually a direct estimate, almost direct estimate of the score field. So it's super easy to train. That's why I mentioned it. It's one of my favorite generative models these days, because it almost always works. If you're interested in what type of architectures you're using for solving these things, it's a standard unit. There is also additional things that you can worry about, like the regularization of this method and all of these things. But you can ask me questions about this afterwards, or look at the paper to know more about this. But the gist is this. So that's how you learn the score. And then I said that even if you knew the score, sampling is difficult. And that's always true. Doing inference in high number of dimensions, this is never something very easy. But the strategy that we use in this project is to use an annealing type of approach. So one way to think about this and why this makes the problem easier is that, let's say that I want to sample from this distribution here on the right. It's very difficult, for instance, for a chain to go from this mode of the distribution to that mode of the distribution. It's going to be very difficult no matter what method you use. But if I add noise to the distribution, so I make it more blurry, if you want, all of the modes start to merge together. And so sampling with a lot of noise here becomes trivial, because you can go through this whole distribution without any problem. So the idea of this method is that you start to add noise to your distribution. It's very easy to sample it here. And then you run the chain and you slowly decrease the amount of noise of your distribution. So your chain is going to get stuck in one mode at some point, but that's fine. You just grab the last point in the chain and you say, that's my sample from this target distribution. And this works super well. And I mean, it blew my mind how well this works. Here is an example of one of those chains running. And you see that it has lots of noise at the beginning, and it goes towards a low noise realization. And it allows you to do sampling very fast and very efficiently in, here there's probably hundreds of thousands of dimensions. Anyway, super cool stuff. And I encourage you to ask me more questions about this afterwards. And here is what happens when we apply it to our problem of estimating a convergence map. So what you see here on the left is one simulation of such a convergence map from a hydro simulation run. This is from Illustris TNG, and it was ray traced by GIU and Ken Osato to make those simulated convergence maps. And here is what the traditional method applied to this map would be able to recover once it's tried to remove the noise and removing the things. So you can guess, and this is actually what was used for DS. So you can recover some of the structure, but you lose all of the details, and you don't know if you should trust any of those bumps that you see in the image. The other method that was used in DS was this Wiener filter. So this time it was using a Gaussian Prior on the signal. And again, I can see that there is correlation with the structures, but it doesn't have the same properties as this map. And again, I mean, with Wiener filter, you can actually get uncertainty estimates, but here it's not clear as well. And this is what I get when I look at the mean of those posterior maps that I'm able to sample from my full posterior, and I recover a lot more detail. So it's more, it's a lot more accurate, let's say, or precise, more than accurate. But what is also very nice is that now I have access to those posterior samples. So I can actually make a movie of the full posterior, and I can have a look at what it looks like. So one thing that you will see right away is that outside of the survey region here, the map is not constrained. So every sample is going to be different in this region. But when I look inside the survey region, it's well constrained by the data. But there are still some places where the solution is not perfectly known. So if I look here, for instance, I can see that it's either one cluster or two clusters here. And by looking at how the movie unfolds, I have a sense of, should I trust the presence of this structure, or could I actually have several possible solutions in this map? So that's the the next order of things that makes it that you can do with this type of approach. So we have applied it to the Cosmos survey, which was done with HST from like a long time ago now, 10 years ago. And it's again in this paper that we had last year. I encourage you to have a look to see more about this, but it will be again in the paper within 2 weeks from now. So that's the main idea, and you can apply it to a lot of different problems. So I don't have time to go into all of them, but just for instance, here is an illustration of using the same principle of physical likelihood and deep linear prior for solving the galaxy deep blending problem. So separating out different galaxies on the sky, or for solving something completely different. So this is an example of applying it for medical imaging from MRI, which you can also write down as a linear inverse problem, and you can solve with the exact same algorithm as what we did here. And you can also get those nice uncertainty quantification things that you could actually not do before. Right, so here is actually the main thing that I wanted to share with you today. And so that's my main takeaway here. What we've seen today is that we can remain within our framework of Bayesian inference. We can get our Bayesian posteriors. And what that means is that we can keep our physical models for things like the likelihood. So we can physically put in our knowledge of the noise, of the PSF, and stuff like that. But we can use those deep generative models to have much more complex priors. And that's also a way to bridge the gap that we had between numerical simulations or existing data sets from a high resolution survey, for instance, and we can use them for doing inference. And in the middle, I told you about this core estimation thing, which is my favorite thing these days, which is extremely scalable and can allow you to do this, to solve this problem in very, very high number of dimensions. So that was the main point that I wanted to share with you, and the rest is bonus. And I will see how much time I have left for this. So maybe, Kate, how much time do I have left? How am I doing with time? Or Abby?
So I think you can go for 5-6 more minutes.
All right, so I'll just show you one more cool application of those generative models, this time for doing cosmological inference. So far, I've only shown you what happens on, like recovering things like deconvolution or inverse problems, but how to use them for cosmological inference. So first, the question is, what is wrong with traditional cosmological inference? Well, here is how you typically go about it these days. So you do a survey. So for instance, you try to measure this gravitational shear that I mentioned before. And what it looks like, there are different ways you can represent it, but you can think of them as maps on the sky of those measurements. So very high dimensional data again at this level. So this you can never analyze. So the first step is usually to compute a summary statistic from those maps. So typically, for instance, the Power spectrum. And here is what you see. This is the Power spectrum of those maps, those points that you get here. And then the way that you do cosmological inference, that you get constraints on cosmological parameters, is by running an MCMC, by looking at this posterior distribution that you can access to, by using this analytic likelihood that tells me, for a given set of cosmological parameters, how do I expect my Power spectrum to be? And so that is fine, that works well, and this is what everybody uses these days, but it has a bunch of limitations. So the first one is that in order to be able to play this game, you need to use very simple summary statistics of your data that are simple enough that you can actually hope to write down an analytic model for what the likelihood is going to be. And this is, even when you do this, there are some additional limitations. You cannot do this for very small scales. And one very interesting point that we have here is that because of those restrictions, you're limited to, you're throwing away a lot of the information actually presented in your survey, just so that you can analyze it. So that's not super satisfactory, but what can we do about this? So you can take a different road. Instead of relying on analytical theory to predict what the likelihood function of your observable given your cosmological parameters is going to be, you can try to use a simulator. And the nice thing about simulators is that you can put in a lot more effects and you can just run them forward, and they can give you full examples of, let's say, those maps on the sky in very high number of dimensions that you actually observe. And you don't have to make the same number of assumptions. And the question has become, how do I perform inference using such a simulator of my physical model? And here, since we're all, again, talking about simulator, you can think again about this concept of implicit distribution. I don't have an analytic formula that gives me the probability of my observables, but I can draw from a simulator. And so that means I have access to an implicit distribution. And that means I can probably do something with generative modeling. And so there are several ways of doing inference with this type of approaches, but the one that I want to mention briefly here is this black box simulator context where I have just the ability to run the simulation. I cannot actually look at what's going on inside the simulation, which we could also talk about. So here is an example of how you would apply it in real life. This is a paper that we had last year doing this experiment on this convergence map that you have here on the left, which came from the dark energy survey from their science verification data. So this is the actual